All right, guys. So I know that we did not go through all of these in the notes yesterday. I think we did sine x and e to the x, but you should be adding this to your notes, right? So you need to memorize this box. We at some point we're going to have a quiz over 9-7 to 9-8, and the first four questions are they might not be in this order, but write the Taylor polynomials for these four functions, and you need the first four non-zero terms and the general term. So I want to label that right here, general term. And make sure that you include the plus dot 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 at the end. I know that seems sort of extraneous and silly, but these do go on forever. The general term is not the final term. It's just telling you like what the pattern is for all of the terms. So take the time to study those. And the 2n plus 1 is like that because we are assuming that this first term is actually n equals 0, and then n equals 1, etc. So that's how that works out for the first one. Okay, and I want to talk about the last one. So sine, cosine, e to the x, we can figure all of those out the long way like we did yesterday, but you'll have them memorized. This last one, 1 over 1 minus x, this might not be obvious just looking at it, but if you look at the terms, this is a geometric series. Remember, in a geometric series, you should be able to take any two consecutive terms and divide them and get the same common ratio. So x divided by 1 is x squared divided by x is x cubed divided by x squared is x. So this is a geometric series, and the reason it represents the rational function 1 over 1 minus x is because, remember, that's like the setup for the sum of a geometric series. So the first term is 1, and the common ratio is x. So it was set up to be a over 1 minus r. So that's why that function is represented by this geometric series. The reason we memorize these is because eventually we will be figuring out, well, what is the Taylor polynomial for x times sine of 2x divided by 4? We'll have to figure out what that is, and we will just build upon what we have here instead of going through the long way of finding all these derivatives and doing really complicated things. So memorize those. We will use them a lot. Okay. Here's another example where we don't have an equation for f of x. They love to give us these for our free response questions. We don't have an equation for f of x, but we do have some pieces of information. We have the function value at 6, the derivative at 6, the second derivative at 6. The reason they're all being evaluated at 6 is because we're going to find an approximation to f of x using a third order Taylor polynomial. It doesn't come right out and say this, but c is equal to 6. The point of tangency, or the center, is 6. Third order means we take it out to 3 derivatives. That's why they gave me out to 3 derivatives. So the way we do this is just saying f of x is approximately equal to. You can write out the function notation if you want, but remember it's f of 6, so negative 3, plus f prime of 6, so plus 4, times x minus 6, because this is like an x minus c situation. And then it would be plus f double prime at 6, but that's minus 5, so I'm going to write minus 5 times x minus 6 squared over 2 factorial. And the final term would be plus 2 times x minus 6 to the third over 3 factorial. That's our approximation for f of x using a third order Taylor polynomial. If that's confusing, you can always start out with just the function notation and then put your numbers in. It gives you more of like a formula to plug into, but I just went straight to plugging the numbers in. Okay, are we okay with that setup? All right, so then the next one says use that polynomial to approximate f of 6.1. So if you're supposed to plug in 6.1 for all of these x's, that just means I'm going to type this into Desmos in a second. I'm just going to say, well, 6.1 minus 6 is just going to be 0.1 in the parentheses. It gives me a little less typing. But I am going to hop over to Desmos and see what this comes out to, because today is all about error. So we want to be able to see like how far off we are. We're going to need our calculator for a bit of this. So I'm just going to type it in. So negative 3 plus 4 times, instead of 6.1 minus 6, just 0.1, minus, let's see, 5 times 0.1 squared over 2 factorial plus 2 times 0.1 to the third over 3 factorial. Did I type that in right? I think so. Yeah. So I'm going to write this answer down. So I'm getting, yeah, that's what I have on my paper. So I'm getting that f of 6.1 is approximately equal to negative 2.624. I'll just write 6 repeating. We normally have a rounding rule of 3 decimal places. I don't always do that for these because we're usually trying to figure out like how accurate are we, how many decimal places do we match up, and so I usually just write down the whole thing. All right, the next part says, is this approximation an overestimate or an underestimate? I can't just compare it to the graph of f because I don't really know what f looks like, but we've had this question before. This overestimate versus underestimate is really a concavity question. Remember, if you have a graph that's concave down, then I'm just going to use a tangent line just to exaggerate it. The tangent line would be sitting above the curve. Even if this is a tangent curve, it would be sitting above f of x. If the graph is concave up, then your tangent line or tangent curve is going to be underneath the graph. So how do we know concavity? We always look at the second derivative. The second derivative, f double prime of 6, is equal to negative 5. So it's negative, it's less than 0. If the second derivative is less than 0, it means that f of x is concave down at x equals 6. And so because we are approximating 6.1, which is near that point of tangency, we can say that our approximation is an overestimate. Meaning, graphically, if I could graph f of x and my curve, my Taylor polynomial, it should be sitting above the actual point at 6.1. All right, are we okay about that? All right. So we just plugged in a number and made an approximation, and that brings us back to error, just like we talked about with alternating series error. There is a little more to do with these because we don't always have something that's alternating. So we can't always just say, the first neglected term is the max error. So there's this new remainder that we're going to look at, but it kind of starts off with the same setup. So the difference between the actual value, the actual f of x, and your approximation, which would be the Taylor polynomial, we say that that difference is equal to r sub n, which is the remainder. I think that's what we called it for alternating series as well. And if I don't use absolute value, if I get a positive or negative, that tells me a bit about whether I have an over or an underestimate. But most of the time we look at this error in absolute value. Just how far off are you? What's the distance between the actual point and your approximation? Taylor's theorem is going to give us a remainder that's referred to as the LaGrange form of the remainder. So we can thank that mathematician for what we're about to learn. Okay, so here it is. Do you already have this filled in as well? Yes? Okay. So I'm just going to add a couple of things to this. So yeah, LaGrange is up there kind of on the left side. What is that? Joseph Louis LaGrange. All right. Taylor's theorem. Here's what Taylor's theorem says. If we have a function, f of x, that has a Taylor polynomial attached to it, so I've got the Taylor polynomial written out, you could cut off the Taylor polynomial at n terms, and then wherever you cut it off, the rest of that would be the remainder, right? Like the actual sum would be my cutoff point plus this extra bit that I left off. That would be like the actual sum or the actual value of f of x. And we have a way to figure out like what this max value is. So part of yours, I think, is boxed in incorrectly. The little part that should be circled where it says coefficient of the n plus 1 term, like the coefficient is the number in front of x. So it's going to be the n plus 1th derivative at this number z, which we'll talk about in a second, over n plus 1 factorial. So you're still kind of thinking like, what's the n plus 1th term? That's going to be my max error. And that's sometimes called the LaGrange error or remainder. So something that we have to think about, our important conclusion here, is this r sub n of x, it's equal to a maximum error. So just like alternating series error is not giving you your exact error, it's giving you like your worst case scenario ceiling of the error, and the actual value is somewhere within this like margin of error. We have to think about a couple of things. This n plus 1 derivative of z, we're trying to figure out what's the max value of that. What's the maximum possible value? We're going to figure that out by either taking a few derivatives until we see a pattern and plugging numbers in to see what is the max value. Or sometimes if it's like a certain kind of function, it's nice and easy. The answer is always 1 or something like that. Sometimes they tell us what this number is as well in a problem. So we want to figure out what is that maximum possible value. And this number z, it says this z is some number between x and c. So z is between the center, like where is the Taylor polynomial attached? Where's our point of tangency? And whatever number you're trying to approximate. So, and the approximation x, I'll say. Like z in the previous problem would be some number between our center 6 and our number 6.1 that we were plugging in. All right, so we'll have to figure out what that max number is, and then the rest of it just kind of comes along for the ride. So there's always an x minus c to the n plus 1, and it's always over n plus 1 factorial. But this thing right here will either be a number or an expression in terms of n that we can work on and simplify. Okay, so let's just do a couple of these problems, and I'll show you what I'm talking about. So this says use Taylor's theorem to approximate sine of 0.1 by the third Maclaurin polynomial. All of those polynomials in the box back here that you had to memorize, those are Maclaurin. They're all at x equals or c equals 0, so they all just have x's. So I do not need to do a series of derivatives to figure out what's the third Maclaurin polynomial for sine. It's this right here. The third one would take me out to the third degree. Those two terms, that's the third order Maclaurin polynomial for sine. So that's another reason to memorize these. It gives you kind of a shortcut. So I'm going to start right there. The third order Maclaurin polynomial is sine x is about equal to, it was the odds. So x minus x cubed over 3 factorial. And I would cut it off right there. And I want to determine the accuracy of the approximation. So the approximation is, okay, plug in 0.1. I'm not actually going to plug in 0.1, but you could on your calculator. You get some sort of number. It doesn't help us with the rest of this. So we get an approximation for this. I know this is off. The question is, how far off is it? And what's like the maximum possible error? All right, so let's set this up. So we're trying to figure out the difference between the actual value of f of 0.1 and my approximation, which was a third order Taylor polynomial for which I plugged 0.1 into. So I like to write P3 of 0.1. And that difference should equal the absolute value of the remainder when n is 3 of 0.1. Do you need something? I think so, but I don't know who's checking. Sure. Or can you get it signed and bring it tomorrow? Like right after school. It's just, you can just get it signed and then bring it tomorrow. It's fine. Okay, so we have this, and then let's write down our formula. So this is a max error. So I always write here less than or equal to, just like I did with alternating series, less than or equal to. Now I don't need to write f of n plus 1. N is 3. So this is going to be whatever the fourth derivative is of some number z temporarily. And then normally this is x minus c to the n plus 1. So it's going to be to the fourth power. we have numbers to plug in for x and c. X is the number we're trying to plug in, 0.1. And c is the center of the Maclaurin polynomial, which is 0. And then it's always over n plus 1 factorial, which in this case would be 4 factorial. So when they tell you which order polynomial to plug in, just like with alternating series, you have numbers for all this. So you don't have a bunch of n's everywhere. So the biggest thing is, let's figure out this fourth derivative of z. So our original function was sine x, right? And you can either take 4 derivatives, or do you remember with sine and cosine what it's going to be? Yeah, if you do it, it should be the fourth one is the same thing as what you started with. If you don't remember that, just like take 4 derivatives till you get there, but it will come out to sine x. Okay, and then now careful with that though. If this were sine of 2x, I can't just do that. I need to remember that there will be like chain rules happening. There will be some number in front of it. But anyway, sine x. And this z that we're talking about, z is sitting between the center and the approximation. So z is sitting somewhere between 0 and 0.1. But here's the great news about sine. The question is not like, it's not actually which one is bigger, sine of 0 versus sine of 0.1, because that's kind of what we're looking at, are the extremes, like which one is bigger. In general, what is the max value for a sine graph or a cosine graph? Yeah, so the max value for any sine graph, whether you actually hit that value or not in this little interval, is always 1. And that's true for cosine as well. So anytime our original function is sine or cosine, we're not really going to bother with doing any sort of math here. We're just going to say, oh, I'll just put in a 1, because we're trying to go with the maximum possible error. We want to say, like, this is how far off we could possibly be, but we know we're actually better than that. So we're just going to sub in the value 1 for the fourth derivative of z. Its max value is 1. And then the rest of this is just simplifying. If you have a calculator, you can pop it in the calculator. If you don't, you do need to know that this is like 1/10 to the fourth over, what's 4 factorial? It's 24. Okay, and then you would need to simplify this again. If it's no calculator, they would be looking for it to be like, so what is that? So put a 10 to the fourth in the denominator. All that means is put 4 zeros on the end of this. And so it's 1 over 240,000. This is our maximum possible error. We know that our approximation is even better than that. And that's actually like really good. All we had to do was use 2 terms there. This seems like a pretty crazy approximation for sine of 0.1, but it must be close enough to the graph to be able to do that. So that is our accuracy. We know we're within that amount. Okay, questions on that one before I go on? Now, 2 things. What if it's not sine or cosine? No phones in the hallway. What if it's not sine or cosine? Then you have to do a bunch of derivatives and like see what the pattern is. And that brings me to this one. Our function is natural log, so we're going to have to do some work here. And they're not giving me n. This is one where I have to find n. So I will use a calculator in the end, but I need to set it up without the calculator. So determine the degree of the Taylor polynomial expanded about c equals 1. That should be used to approximate ln of 1.2 so that the error is less than 0.001. Okay, so let's just set this up to begin with. I always like to set up this formula because it gives me like direction, like where am I supposed to be going with this? So we are trying to approximate f of 1.2. It's telling me to plug in ln of 1.2. And we're going to approximate that with some sort of Taylor polynomial, but I don't know the n, so I'm just going to write p sub n of 1.2. That's equal to the remainder sub n of 1.2. And I'm just going to write the formula out because I don't have n's, so the formula should be that this is less than or equal to f of n, the n plus 1th derivative, fn plus 1, of some z. Figure that out later. X minus c will be 1.2 minus 1, because that's the center, to the n plus 1 power. and it's going to be over n plus 1 factorial. Okay, so then once you get it all set up, the next step will always be figure out what number or what expression you're going to be putting in for this n plus 1 of z. And when it's not a sine or a cosine graph, you just need to take some derivatives until you start to figure out a pattern. So start here. F of x is ln x. So the first derivative, we did this a bit yesterday. What's the derivative of ln x? 1 over x. We're not plugging anything into it. We're just trying to get a pattern for the derivatives. So then what's the second derivative? I usually have to do, I don't know, 3 or 4 maybe. We'll see. Take the next derivative. Okay, do one more and then we'll see if we want another one. I think the powers of x are pretty obvious, right? Could you write a general formula? Let's do Fn. For the nth derivative, the denominator is definitely x to the n, right? Do you see the pattern in the numbers yet? We might not have done enough. Don't worry about the negatives. Yeah, they are factorials because every time you are taking the previous number and multiplying it by next exponent. If you don't see that yet, if I just do one more, usually this gets it. This next one would be 24 over x to the 5th. You are going to see 1, 1, 2, 6, 24, 120 pretty often. Eventually it will catch on that that's n factorial. So the top, let me stop writing this, so weird. The top is n factorial. And we do not care about the alternating because remember, all of this is an absolute value. So don't worry about the alternating part. Okay, now I'm not supposed to plug in Fn. I'm supposed to do n plus 1. So once you have this formula, go ahead and plug n plus 1 into it. Oh, wait, sorry. Is this n factorial? Yeah, it's not actually n. This is, the fifth derivative was 4 factorial. The fourth derivative was 3 factorial. So, sorry. You should write down the right formula. N minus 1 factorial. Okay, so then plug in n plus 1 into this. N plus 1 minus 1 becomes n factorial. And it would be over x to the n plus 1. And I'm not ready to plug this in yet because you cannot have an x in this remainder over here. You've got to have everything just in terms of n's or numbers. So now we need to actually pay attention to this like z number. So z is sitting between the center and the number we plugged in. So the center is 1, number we plugged in is 1.2. You never have to worry about the numbers in between those ends. You're always going to be looking at the extremes. So these are numbers that we would be putting in for x. So if z is 1, then we get n factorial over 1 to the n plus 1. If z is actually 1.2, we get n factorial over 1.2 to the n plus 1. Compare those fractions. What's my inequality symbol here? Like which one's smaller or bigger? Okay, left is larger. I guess we don't have to put an inequality symbol in, right? Circle the bigger one. Boom, that one. Because if you divide by a larger denominator, you have a smaller overall fraction, right? That's really good because that is much easier to sub in to here than the one with the 1.2. N factorial over 1 to the n plus 1 is really just n factorial, right? 1 to the n plus 1 is just 1. That means that we did all of that work, but it means that we can just put in an n factorial right here. That's the maximum number that you could get. N factorial for that spot times, how about we just make this 0.2 to the n plus 1 over n plus 1 factorial. And I forgot to say, once we get this all figured out, we're trying to figure out what n is to keep this less than 0.001. We can cancel some stuff out, right? That should always happen. N factorial over n plus 1 factorial. So now it's 0.2 to the n plus 1 over just n plus 1. If I have a calculator, I can start plugging stuff in. If I don't, I need to work on this. 0.2 is 2/10, which is 1/5. So you could also write this as 1 over 5 to the n plus 1 times the quantity n plus 1. And you're trying to get that to be less than 1 over 1,000. So in other words, if I don't have a calculator, I'm just going to plug some numbers starting at 1 into the bottom until I get something bigger than 1,000. If I do have a calculator, I'm going to hop over to Desmos. Oh, maybe. There we go. And I'm just going to do the 5 part. So it was like, I like to do it like this. F of x equals 5 to the x plus 1 times, was it x plus 1?
Yeah.
And then I just like to start plugging in, like, is it 1? Probably not. Is it 2? Is it 3? 3. 3 gets me to a number bigger than 1,000. So it escalates pretty quickly, especially if it's something that could have been non-calculated. See you later. Okay, so that was, oh, what happened here? So that was 2,500. So when n equals 3, we got this to be 1 over 2,500, which is definitely less than 1 over 1,000. And the question was, what degree should this be? So remember, order is not always the same as degree, but it is the same as degree as long as your derivatives aren't coming out to 0. So remember, the center is at 1. If you plug 1 into any of these, you're not going to get 0, so you will have no 0 terms. So if you take this out to third order, it will be third degree as well. So that is the degree as well as the order. All right. We're going to try homework number 22 and see how that goes. Error can be confusing, so I would use these notes as you're going through it. And we'll just practice for the next couple of days too.